When physical structures fail, the collapse is usually the result of a framework unable to handle structural stress. Software engineering follows a parallel logic. Applying an inflexible development framework to a highly volatile project creates a momentum that often leads to failure. Imagine you step into a role as a lead software engineer, and your director hands you 3 massive concurrent projects. Each one has vastly different constraints, and you have to map out how your team will build them. Project 1 is a library management system. The school knows exactly what they want. The system requirements are absolute, the data structures are defined, and the inputs are predictable. Project 2 is a brand new social media application. The client has an initial concept, but they explicitly state that they expect the feature set to change continuously based on user engagement as development progresses. Project 3 is writing the telemetry software for a satellite. Here, a single runtime error translates to millions of dollars lost and total mission failure. Can you apply the exact same development methodology to all 3 of these systems? The short answer is no. Attempting a one-size-fits-all approach across projects with such distinct risk profiles is a primary driver of engineering failure. There is no universally best software process model. Instead, the correct methodology is a deterministic choice based on 4 critical input variables: requirement stability, customer involvement, risk tolerance, and project complexity. Let's look at how to determine the right approach. This top-down flowchart represents our first architectural framework, the waterfall model. Its entire structure relies on one strict constraint: the software requirements must be locked in and completely fixed before any coding begins. The defining operational rule here is strict sequence. An engineering team must completely finish one distinct phase, document it, and approve it before the next phase is allowed to begin. Because this path is perfectly linear, going backward to adjust for new ideas is highly disruptive. As a result, customer feedback and involvement remain low once the actual development cycle starts. This rigid structure explains why waterfall is a logical choice for stable, predictable tasks. Returning to our initial examples, systems like a payroll processor or a library database are well suited here because their core logic rarely shifts. The waterfall model deliberately trades flexibility and adaptability in exchange for sequential predictability. But predictability is a luxury. If your client comes to you with a vague concept and cannot articulate exactly what the final software should do, a linear model will likely lead to a product that misses the mark. This circular feedback loop illustrates the prototype model. We shift away from a rigid timeline and move into an investigative cycle designed specifically for requirement ambiguity. We prioritize extreme customer involvement early on. By building a fast, low-fidelity sample of the interface, we give the client something tangible to test, allowing us to extract concrete technical requirements from their feedback. It is vital to understand that the prototype generated during this phase is not the final software product. It is a disposable mock-up meant to answer questions, not process live data. The prototype model functions as an exploratory tool. It accepts early inefficiencies in coding to improve the clarity of the project's final requirements. If your objective is capturing immediate market share, like launching a competitor to WhatsApp or Spotify, building a disposable sample isn't enough. You need functioning software in the hands of users quickly, while retaining the ability to morph the product based on live data. This graphic demonstrates the evolutionary model. It is engineered specifically for environments where feature requirements will continually change, even after the project launches. The critical operational difference between this and the prototype framework is deployment. The evolutionary model builds a working, fully functioning core application and releases it to the live market immediately. Once version 1.0 is stable and serving the public, the team gathers data and begins coding version 2.0. The software scales outward, adding features version by version, while the foundational core remains operational. By prioritizing speed to market over strict upfront planning, the evolutionary model becomes an engine of adaptability for growing consumer software. Speed and adaptability are secondary in high-stakes engineering. When we look at software controlling commercial aircraft navigation, the error tolerance drops to zero. We see the same risk profile in systems driving critical medical hardware or defense grids. A bad update cannot simply be patched tomorrow. A failure here can result in the loss of life. This four-quadrant spiral visualizes the spiral model. It is designed exclusively for massive, complex, and high-risk projects. Its defining signature is the second quadrant, a mandatory, rigorous phase dedicated entirely to risk analysis. Because both frameworks loop, it's easy to confuse the spiral model with the evolutionary model. The distinction is in the constraints. Evolutionary moves as fast as possible to push out an update. Spiral requires intense risk mitigation before a single line of code is written for the next phase. The spiral model treats risk reduction as a mandatory structural checkpoint. If a risk cannot be mitigated, the model dictates that the project should not proceed. Understanding these four frameworks is only half the job. A lead engineer must convert these theories into a strict protocol to ensure they assign the right model to the right project. This code block represents the mental decision tree. We define a selection function that evaluates our project variables as inputs. The logic executes in order. If the project requirements are absolute and fixed, the system selects waterfall. If the client is unsure of what they want and requirements are unclear, the logic points toward prototype to extract that data. If the project carries severe physical or financial danger, the protocol prioritizes safety and selects spiral. And finally, if the product requires continuous iteration and multiple market releases, the logic selects evolutionary. This pseudocode strips away the aesthetics of a project. By looking only at the structural constraints, the correct framework becomes clear. Let's run the telemetry software through the logic. Because the risk is flagged critical, the logic bypasses the other models and selects spiral. If we test our library management system, the known fixed requirements immediately trigger the first condition, confirming waterfall. When we consolidate all of this data, we generate a master comparison matrix for systems analysis. To retain this matrix, link each model to its functional keyword. Waterfall requires fixed parameters. Prototype builds a sample. Evolutionary scales inversions, and spiral mitigates risk. Misaligning a project with its structural framework wastes resources and increases the likelihood of failure. Matching the model to the constraints is what protects the project's integrity. As a lead engineer, you do not adapt a project to fit a favored process model. You analyze the variables and select the process model required by your project's constraints.